Hello students, welcome to Abdemi's YouTube platform. Based on your feedback, I am considering two MCQs from Oscillation in this session. See the problem. These are very simple problems but interesting. A particle executes simple harmonic motion with a frequency f. The frequency with which its kinetic energy oscillates is which one is correct. So let the particle execute simple harmonic motion with a frequency f. Say let us simplify the situation like this. Say this is the equilibrium position, this is x-axis, and the particle is executing simple harmonic motion with amplitude a. So it oscillates between 2 points. This point is x equal to a. This is x-axis. This is y-axis. This is executing simple harmonic motion. Mass is m. Say, and it is oscillating between 2 points a and a dash, whose coordinates are a0 and negative a0. So I can write x as a sine omega t. This is the equation of connecting x and t. T is the time, x is the displacement from equilibrium at t equal to 0, x equal to 0. So this is the equation of motion, you can say. So dx dt is the velocity of the particle, which is function of t, is a omega cos omega t. So kinetic energy of the particle is half a v square, is m by 2 a square omega square cos square omega t. So it is how much? M a square omega square by 4. If I write, then it is 2 cos square omega t. Now you know cos 2 theta is cos square theta minus sin square theta. Simple trigonometry. So it is cos square theta minus 1 minus cos square theta. So 2 cos square theta minus 1. So 2 cos square theta I can write 1 plus cos 2 theta. So I can write m a square omega square by 4 1 plus cos 2 omega t. So kinetic energy, if I write k, it as k. So k is a function of kinetic energy. If I call this as k, then k is a function of t, and it fluctuates with time. And since it is k has a constant term, m a square, not m square, m a square omega square by 4 plus m a square omega square by 4 cos 2 omega t. And because of presence of this cos 2 omega t term in the expression for kinetic energy, k is a function of time, and it in a cosinusoidal manner k value is changing, and the frequency of oscillation of kinetic energy is obviously 2f, where f is omega by 2 pi. Because omega here it is given with frequency f, that means omega is actually 2 pi f. So the kinetic energy, which is a function of time, this is a constant term and this is a time dependent term, and time dependent term varies cosinusoidally. So at the frequency of oscillation, since because of the presence of cos 2 omega term, frequency of oscillation of kinetic energy is twice of f, because there is presence of 2 omega term. You can plot k versus t graph and you can see that it fluctuates with frequency 2f. So kinetic energy of the particle is function of time and it oscillates with frequency 2f. So 2f is the correct answer and therefore answer is C. Okay, so it is quite interesting that kinetic energy is a quantity pertaining to this motion, which is also fluctuating with time, and frequency of fluctuation is twice of f. F is the frequency of SH. Okay, so this is interesting. I hope it is clear. Very simple but quite interesting. Next problem. T1 is the time period of a simple pendulum. So consider the pendulum whose length is L and acceleration due to gravity is G, say. Then time period T1 equal to 2 pi root over L by G. And G is actually 10 meter per second square. G is given 10 meter per second square. So it is 2 pi root over L by 10. Q1 equal to 2 pi root over L by G. L by 10 rather. Now the point of suspension, this is the point of suspension of the pendulum, moves vertically upward according to y equal to kt square. So this is the point of suspension of the pendulum and this point is moving vertically upward following the equation y equal to kt square. Y is the displacement of the point of suspension. So dy dt, velocity of the point of suspension, which is upward velocity of the point of is equal to 2 km. And d2y dt square acceleration, which is also in the upward direction of the point of suspension, is 2k, sorry, is 2k. But k value is 1 meter per second square. So it is 2 meter per second square. So acceleration of the point of suspension is 2 meter per second square. Since the point of suspension is moving up in upward direction with acceleration a equal to 2 meter per second square. So the effective G will be how much? If I call this G dash, effective value of acceleration due to gravity. Effective acceleration due to gravity G dash becomes G plus A, that is 12 meter per second square. Okay, so now what is the period of oscillation? So T2 is 2 pi root over L by G dash, that is 2 pi root over L by 12. So T1 square, the new time period is T2, then what is the value of T1 square by T2 square? Which one is correct? So T1 square by T2 square is 1 by 10 multiplied by 12. So it is 6 by 5. So 6 by 5 is the correct answer. So answer is B. Okay. So when the point of suspension move in the upward direction with acceleration A, so what happens? Let T be the tension of the wire through which the bob or mass is suspended. So what happens? T minus mg becomes ma. So T is mg plus A. When it is moving upward with acceleration. Normally here T is equal to mg. But when the point of suspension moves in upward direction with acceleration A, then tension becomes mg plus A, and as a result, the acceleration due to gravity effectively becomes G dash, which is G plus A. So G is 10 and A is 2. So G dash is 12. So from which you could find. So this is also a very simple problem. I hope you have understood. So thank you for listening to this problem. Thank you once again. We will consider a few more problems in subsequent sessions. Thank you very much.